Okay, cool.
Okay. Okay, so now, yeah, I think Harrison, you can, yeah, exit your slides and we will start. Yeah. Okay, so I think we will start our session this time, and our session is about software validation and verification. And in this session, we will have 4 talks, and each talk will be have 5 minutes, and after the 4 talks, we will have around 40 minutes to discuss with each other, and we also very welcome any question from the audience to give the to ask communicate with the authors, and I will also help read out some questions if the audience only test the questions in the chat. So okay, so let's start. I think the first talk will from Rong Chen, and he will talk about data-driven loop-bounded learning for termination analysis. So now I give the time to Rong Chen.
Okay. Thank you. Yeah. Hello, everyone. I'm Xu Rongchen from Tsinghua University. Today, I'm glad to show our recent work on program termination analysis. The termination is a crucial liveness property for a program. A lot of work has been devoted to the analysis of program termination for a long time. However, termination analysis is still challenging. The data-driven method has been applied to many fields in recent years and has shown its unique advantages. In our work, we attempt to integrate data-driven approaches with the termination analysis. Look at the right program with a single loop. In the loop, the variable x keeps increasing when it is less than 10, otherwise it will be reset to 0. Obviously, the program is always terminating, but how can we strictly prove it? For all input x, we can find that the loop must iterate no more than m equals minus x plus 11 or 1 times before finishing. We call such the m a loop bound for the loop. This is the main framework of our approaches. Initially, the default loop bound m equals 0, and the dataset h is empty. In the analysis, we will generate a verification task for the current loop bound m and check whether it is valid. If the current bound is valid, we can report the program terminates. Otherwise, we can produce a counterexample during the constraint solving and update the dataset. Then we can learn a new bound and repeat the procedure. There are two critical problems here. One is how to learn a loop bound, and the other is how to check the loop bound. We will further discuss them in the following slides. We use a random test to generate the data for bound learning. During the test, we collect 2 kinds of information. One is X, the program states at the loop head. The other is IDC, which represents the remaining number of iterations before the execution terminates. Thus, the loop bound learning problem is to find a loop bound candidate M such that for all data in dataset, Mx is greater than or equals IDC. Our paper proposed 3 kinds of loop bounds, including simple loop bounds, conjunctive loop bounds, and lexicographic loop bounds. In this presentation, I will introduce the first 2 bounds briefly. Suppose the current dataset for the right program is the triangle nodes. We can apply a simple bound learning here. The simple bound learning is an optimization problem. The optimization target has 2 terms. V cost makes the bound result closer to the data points, and M cost makes the form of the result more simple. However, one simple bound may not fit the whole dataset tightly. Thus, we propose the conjunctive loop bound learning to learn more local features. Our conjunctive bound learning will use a clustering algorithm to convert the problem into several simple bound learning problems. After the bound learning, let's consider how to validate the bound. Given a program and its loop bound candidate, we first transform the bound validation task into a safety property problem. For example, we inserted the right code into the original program. Then we made a bounded model checking-based quick bound check, that is, unrolling the loop k times and checking whether the bound is correct. The quick bound check will help us falsify an incorrect loop bound in a short time. Finally, we use a safety checker to generate an invariant and exhaustively prove the loop bound. Note that our invariant synthesizer is also data-driven, so we can show the data between bound and invariant learning and make the termination analysis more efficient. Based on our approaches, we implemented a prototype tool called DDL10. We compare our DDL10 with the art termination analysis tools. Our DDL10 solved 136 benchmarks, and the average solving time was 5.43 seconds. In the figure of cumulative time for solving benchmarks, our DDL10 extends further in the solving number and grows slowly in the cumulative time. That's all of my presentation. Thank you for listening.
Okay, thank you, Rongchen. I think we will have more discussion later. So the next speaker will be the Samantar. She will give the presentation about evaluating commit message generation. So Samantar, you can share your slides.
Yeah, sure.
Okay, we can see it. Yeah.
Fine. Okay. Hello. Good day, everyone. I'm Samantha, a second-year MSc Data Science student at Chennai Mathematical Institute, India. Today, we are going to talk about our paper, Evaluating Commit Message Generation to Blue or Not to Blue. I would like to thank you all for being present here and watching this presentation. I would also like to thank my co-authors, Dr. Venkatesh Vinayaka Rao, Dr. Monica Gupta, and Sampath Deju. Software developers are well acquainted with a patch or a software patch, which is nothing but a code change associated or accompanied by a reference message or commit message, which explains the code change. There exist several commit message generation models that take code changes as input and outputs commit message, such as CommitGen, NNT, NNGen, etc. Our paper primarily focuses on the evaluation of such automatic commit message generation models and tries to improvise the metric used for such evaluations. Literature survey reveals that BLEU-4, which is primarily a machine translation evaluation metric, is most popularly used for evaluation of such commit message generation models. But since the structure and semantics of commit messages is different from that of standard English sentences, BLEU-4 doesn't seem to be the best one for the purpose. In fact, none of the existing metrics that we have used for machine translation or natural language generation seem to be a good match. Our paper thus introduces a novel metric log-mNext for the specific purpose of commit message generation model evaluation. In our paper, we followed a three-step approach in constructing our new metric in the form of three research questions. The first step was to identify some 6 potential factors after extensive literature survey which could affect the commit message generation quality such as length, word alignment, case folding, punctuation, etc. Then, finally, we chose 5 factors out of these 6 chosen factors as valid factors to be considered in our formulation based on correlation with human annotated dataset. The second step was to form the new metric based on incorporating all the desired factors identified in step 1, and thus log-mNext was created. The log-mNext is a revised version of the popular Meteor-Next metric, which was devised by Densky and Levy back in 2010. We'll look at the formulation of log-mNext shortly. Finally, the final step was to use our new metric on the existing commit message generation models and see which model performed the best when evaluated using the log-mNext metric. And we noted that NNGen performed the best in this respect. The structure of log-mNext incorporates exact stemmed and paraphrased word matchings. It also performs string lower casing and punctuation removal as pre-processing steps, and finally assigns a 0 penalty score in case of exactly similar pairs of reference and predicted sentences. The formulation looks quite similar to the Meteor-Next metric, except that a few changes have been brought about internally and a few additional modifications have been done. Now, there have been works comparing automatic evaluation metrics for machine translation, but none of them have talked about the need for a new metric altogether. And in this respect, our work stands superior or different from the existing ones. Nevertheless, we now have a long way to go in terms of building a larger human annotated dataset which contains more reference and predicted pairs, working on learning-based metrics by bringing them into the comparison, revising the structure of the metric to accommodate better case folding and paraphrase matching, etc. And finally, building an exhaustive commit dataset including more programming languages. I would like to conclude by emphasizing that researchers and developers should henceforth discard the use of BLU4 and its variants for evaluating commit message generation and rather enforce the use of a more generic metric, our novel metric log-mNext, for the same. I encourage you to read our paper for more details, and thank you.
Okay, thank you, Samantha. I think, yeah, thanks for the talk. I think we will move to the third talk from Yanjie that's about REFT refinement types for valid deep learning models. So, Yanjie, you can share your slides.
Okay. Hello, everyone. I'm Yan Jie. I will presenting our work REFT, refinement types for valid deep learning models. This is joint work with Zhengxian Li, Haoxiang Lin from Microsoft Research, Hongyu Zhang, Mingwu from TreeGraph Blockchain Research, and Mao Yang from Microsoft Research. Deep learning models provide many configuration options for users to tune. For example, the hyperparameters, neural architectures. Let's see an example. This is a CNN model. It contains several modules, and each module contains several cells. Subgraph, each node represents a count2D operator. User can tune the kernel size, which we use the red font to mark it. User can also tune the subgraph architectures. Each graph represents a combination of configuration, and the user will train it and get the learning performance. For example, the accuracy. Then user can find the best model and train a long epoch and to get the final model. But the deep learning also contains many type errors like the traditional program. For example, the DR models constants, variable, and methods. Recent empirical studies indicate that type errors of not uncommon. We list two representative empirical study. The first one is the dataset is from Stack Overflow and GitHub. The second one is from the production deep learning platform. We also we see that the incompatible shape, tensor shape and tensor mismatch is very common. For example, the second one, it is class of DR-specific job failure root cause. So we think that this is a very critical problem. Let's see an illegal shape error example. We list PyTorch as a popular deep learning framework. Red DR model is a CNN model which can do the object detection, image classification problem. This model will trigger an illegal shape error. The reason is that the NN's average put2D operator user size, the kernel size is very large. So that the height and width of the output tensor will be negative. It will trigger a runtime error. So reducing type errors of DR model is very important. Significant shared resources is especially on the platform, first party or third party on the cloud, and boost development productivity for end user, reduce failures for deep learning training jobs, benefit AutoML tools to improve search efficiency. But it is very challenging because the hybrid programming adopted by DR frameworks has internal computation. We user write the program in Python, but lose the tensor shapes. We can't directly pass the Python code to get that. There is a large number of possible hyperparameter combinations and neural architectures. User use the AutoML tools to define the search space will be very huge when the search space become large. So we also summarize the common type errors of deep learning models. It contains two large dimensions, hyperparameter error and tensor error. Hyperparameter error contains two categories. One is the illegal value, other is the improper value. The tensor error contains four categories: illegal shape, incompatible shape, and incompatible element type. So we propose Rafty, try to solve that error detection problem. So we propose the refinement tabs for valid DR models. Rafty will refine each operator with logical formulae that describe the computation requirements on both tensors and hyperparameters. It can checking the validity of a model is reduced to a constraint satisfaction problem. Rafty utilizes SMT solver to obtain the unsatisfiable hyperparameter values before job execution. Let's see an example of the refinement types of MATML operator. Other operators example is complex and we list on the paper. We ascribe MATML the matrix multiplication of function type. It is also called the operator in the framework, specifying that it accepts two input tensor parameter denoted by S1 and S2 and produces one output tensor parameter denoted by Y. So P1, P2, and P is the constraint that for each tensor S1, S2, and Y, it will constrain shape, order, and element type. Rafty Rafty is a tool, so it contains a workflow. Rafty accepts a computation graph, model specification, tool specification as input. Then it will traverse the computation graph following the operator execution dependency to generate a set of constraints that the DR model should satisfy. We also evaluate the RAFT's effectiveness on individual DR operators and real-world DR models. We also evaluate the efficiency in constraint solving, comparison with related work PASEA. We use the precision recall and the speed up to measure RAFT's effectiveness and solving performance. So we list evaluation. The first one is that we tune the hyperparameters. For example, the kernel size, thread, and operators, COM2D and MASP2D to measure the effectiveness on real-world DR models. RAFT achieves 100% precision and recall in all the experiments, confirming its effectiveness. We notice that there is a discrepancy in the ground truth of VG16 experiments, whose root cause comes from the differences between the official training program for PyTorch and the TensorFlow. We also compare RAFT with PASEA. PASEA is a static shape checking tool to test compatible shapes for TensorFlow Python programs. Other tools.
Sorry to interrupt. I think the time. Please count your time. We will have the 5 minutes limit.
Okay. I have reached the
final
page. Thank you, everyone. Sorry.
Sorry. Okay. Yeah. Thank you, Yanjie. We will discuss more later. I think we will move to the last talk, the fourth talk from Harrison about GraphFuzz, library API fuzzing with lifetime aware dataflow graph. So Harrison, you can share your slides. So Yanjie, can you exit your screen sharing? Okay.
Okay. All right. Hi, I'm Harrison, and this is GraphFuzz library API fuzzing with lifetime-aware dataflow graphs. This is work that I did at For All Secure, along with, and I'm really excited to be able to share it. Okay, so the problem we're trying to solve is how to test APIs automatically. And in this work, we focus specifically on C++ libraries, like this example here, but a lot of the concepts apply more generally to other APIs. So one of the well-established ways to do automated testing is called fuzzing. And the idea with fuzzing is you define a wrapper function, like this fuzzme function here, that takes some chunk of data and does something with it, like maybe it calls a parse image function. And the idea is that the fuzzer will invoke this function millions of times with different data to explore the state space of your target. But in a lot of APIs, like in this mock canvas example here, there is no convenient entry point that accepts a big chunk of data. And instead, we're interested in testing the interaction of many small functions. So how can we do that? So with GraphFuzz, the main idea is to represent API interactions as dataflow graphs. And so in the graph, vertices represent API endpoints, in this case, functions, and edges represent objects that are produced by some endpoints and consumed by others. So for example, here we have a method on a canvas object. So as input, we need a canvas object and a point object. And after we invoke this function, we're free to do other things with the canvas and point. So they would also be outputs. So in general, you can imagine converting your whole API surface to a set of endpoints with expected inputs and outputs. For example, here we have a canvas constructor that produces a canvas object. And similarly, we have a canvas destructor that consumes a canvas object. And with this representation, the problem of generating a new test case becomes, how can we link a bunch of these endpoints together such that all of the edges are connected and match with each other? So an example of a complete dataflow graph representing a single API interaction is shown here. On the right, we have our graph representation with vertices and edges. And on the left, we have equivalent C++ source representation. Notice how on the right, all of the edges are fully connected and all of the types match. Additionally, with this representation, we can be sure that we're doing proper object creation and deletion. For example, we can be sure that we're invoking our canvas constructor before calling canvas draw point. And similarly, after we invoke canvas draw point, we can be sure that we're calling our canvas destructor. Additionally, this representation lets us perform high-level structure-aware mutations on the API sequence itself. For example, here we've added 3 new function calls and we've properly linked it into the graph. On the left, you can see what the equivalent change at the source code level might look like. Importantly, with GraphFuzz, we can perform this mutation and then execute the resulting API graph without recompiling with a process that we call dynamic execution. And this lets us very efficiently mutate and test new API interactions. So during our research, we applied GraphFuzz to a bunch of open source libraries, and we found bugs in nearly all of them. So here are 4 examples of crashing test cases that we found with GraphFuzz. Skia is a graphics library used in Chrome and Android. RDKit is a cheminformatics library written in C++, and SQLite 3 is a database library written in C. It's worth noting that all 3 of these projects are included in OSS Fuzz, and yet GraphFuzz was able to fuzz new APIs and find new bugs. So using GraphFuzz is fairly straightforward. The first step is basically to define a schema, which contains a list of all of the objects and methods that you want to test. And in the majority of cases, it's actually sufficient to just list all of the function signatures you want to test, and GraphFuzz will automatically infer the inputs and outputs. In some cases, it's necessary to be more explicit, and so we also have a more verbose definition. You can refer to the pre-recorded presentation or documentation for more details about that. Once you have a schema, you use the gfuzz command line tool to automatically generate harness files, and then you can compile them with Clang using the fsanitize fuzzer flag. And this produces an executable that you can run to start fuzzing. As a bonus, because GraphFuzz uses libfuzzer under the hood, the generated executable is a native libfuzzer binary, so it automatically works with any fuzzing as a service infrastructure like OSS Fuzz. And finally, GraphFuzz is completely open source under an MIT license. We've included a bunch of Docker files with all of the fuzzers we built during our research, and we've set up a website with some documentation and introductory tutorials to hopefully make it easy to learn. Contributions are definitely welcome, so if you have questions or ideas for improvements, please open an issue or submit a PR. Thank you.
Okay, thank you, Harrison, for the talk. Okay, now we have finished all the presentation, the 4 presentation in this session. So we will enter into the next stage that we will have 3 discussions that I think we have still have around 30 minutes. So yeah, I note that we have a number of a few audience in our room. So just feel free to post your questions to the authors, and I think the authors can also ask each other if you also have some questions. Yeah. Yeah, I think maybe because some issue about my browser, I cannot see some questions from the audience that's posting the chat channel. So Jonathan, if you saw someone, you can also help me that read them out. Yeah.
Yeah, I can do that. There's no questions yet in the chat, but when it comes along, I'll mention it.
Yeah. Maybe you can help me raise that question. Oh, okay. So maybe we can quickly the 4th speaker, you can quickly give 1 sentence summarization of your work so that to remind the audience. Maybe we can start from Rongchen. Just quick 1 sentence summarization. Yeah.
Okay, our work use a data-driven method to learning loop bound and we loop bound for termination analysis. We propose the 3 kinds of loop bound learning and improve the validation for the loop bound. Yeah.
Okay, thank you. So Samartan, can you also quickly summarize with 1 sentence about your?
Okay, so our work basically deals with evaluation, rather automatic evaluation of commit message generation models and revising or improvising the metric used for the purpose. We want, through our study and research, we want to encourage the use of a new and novel metric proposed in our paper, which is log mNext, instead of the popularly used BLEU4 metric for the purpose. Yeah. So that's
Okay. Okay, thank you. So Yinjie, can you quickly, summarize?
Type errors for deep learning are uncommon. We propose Rafty refinement types for valid deep learning models.
Mhm.
Thank you.
Okay, thank you. So Harrison, maybe you can also quickly, summarize.
Sure. So the idea with GraphFuzz is to represent API interactions as data flow graphs so that we can fuzz things like C++ libraries.
Okay, thank you. Yeah. So now we have, let's the speaker quickly summarize their talk. So if you have questions, just unmute yourself and ask. Yeah. So maybe I can first start ask some questions. So Rongchen, that I listened to your talk and I note you mentioned you have a benchmark to validate your tool. I note that, but I note that you cannot handle all the cases. So is there any reason that to explain that's why you cannot handle all the termination analysis cases?
Yes. First, the termination analysis is still challenging. Yeah. Currently, most tools cannot solve these all benchmarks. It is mainly because the first the termination analysis is the hunting problem. It is undesignable. Yeah, our method is to find a proof. Try our best to find a proof. So it is impossible to prove all the program terminates. Yeah.
Okay. Yeah, I note Thanasis is also listening to your answers. I'm not sure whether you will have some questions.
Yeah, I'm not sure if my audio works. Can you guys hear me?
Yes, we can hear you. Yeah.
Hello. Yeah, I just wanted to say it is always refreshing to see work that is trying to solve these hard problems, because you go to school, you hear about the halting problem, and you're told this is impossible, and here you are. There are tools that can achieve this on not in the generic sense, because we know there are hard bounds. But one question I had on this, Rongchen, would be, what is the limit? Like, if you had to quickly, I guess, describe to us, what is the limit in terms of programs that we can analyze using this, in terms of size or maybe complexity? I don't know if you have any numbers off the top of your head.
Yeah. First is the size of the program is very important. Yeah, if the program is complex, we cannot. It's not easy to find termination arguments such as the loop bound or the ranking function. So it's not possible for us to prove the termination. The other is also the program always are different from each other. We sometimes we can't find a general methods to cover the all situations. Yeah.
And then that completely makes sense. In each program, like, you can write a very short program, a one-liner that is horrible, and maybe it's very hard to reason about its termination. But in your benchmarks, for instance, were these benchmarks mostly, were they 100-line programs? Were they 1,000-line programs, or a billion-line programs?
It's almost in 100 lines. Most of them are 30 to 50 lines. Yeah.
Oh, okay.
Perfect. Thank you.
Okay, thank you, Thanis. Yeah, I note that we also have other audience that Tevfik. Maybe you can say hello to. Oh,
I thanks for the nice work. I just wanted to ask, so for the backend constraint solvers, expressiveness of that, I assume, impacts what kind of loops you can analyze, and there are different theories, and so are you looking for only arithmetic constraints, or can this kind of analysis be used for other theories? So I'm looping, for example, let's say I'm looping over a string and I'm doing one character at a time. That kind of, or is it, so what kind of theories backend solvers to use for this?
Yeah, we solved the program with integer variables, and the only theory we use is the integer theory.
Okay, thanks. But do you think, I mean, is there possible generalization to other theories? If you had a constraint solver that handled string theory, would the method applicable to termination of the other types of programs?
I think the it's may possible to generate to the other theories, but the hard problem is how to describe the termination arguments, like in our paper, the loop bound or the ranking function. Use this if there is no integer variables like the arrays, how to describe this the termination arguments of these items? Yeah.
Good, thanks.
okay. Thanks. Question from Tevfik, and also thanks Rongchen to answer this question. I think we have a much more deeper understanding of your work. That what's the limitation and also the possible future direction to make the work more practical. Yeah. So we can move to the if the audience do not have any more question, we will move to the next speaker.
Yeah.
Okay.
There's actually one question in the chat from Samantha.
Okay.
To Harrison, which was, or you can read or I can read it, but see.
Sure, I can read it.
Yeah.
So
Harrison, you can directly read the question, and also.
Or Samantha, yeah. She's.
Yeah. Oh, Samantha. Okay. Mm-hmm.
I'll read it for him. So was there any significant notable difference in your findings, Harrison, for the 4 open source libraries that you analyzed?
Yeah, so in general, the types of APIs that we were testing in the different libraries were pretty different. So like if you think about like a graphics library versus a database library, the functions themselves do very different things. I think one thing that was pretty surprising was how easy it was to find crashes. For example, you don't even need to call very many different functions. You could call maybe 5 or 6 functions in a row and get a crash. And I think that's really shows how people aren't testing in this way already. So there's a lot of untested code and just in low-hanging fruit in this space. I think another thing that was interesting was we found a lot of crashes across all of the things we tested that are due to deleting some object, and then some other piece of the code was trying to use that object that had been deleted. And I noticed that when people write unit tests, people generally don't delete objects during the middle of the unit test. So you might not find these bugs in more traditional ways. So those were the main things.
Okay.
Thanks. That makes sense.
Mm-hmm. So yeah, maybe I have a follow question for Harrison first. That I noticed you have some data flow information to leverage the data flow information to do fuzzing. So do you first need to use some static analysis to construct some data flow graph?
Yeah, so instead of doing, some previous works have done static analysis on API to construct a data flow graph. With GraphFuzz, we start with a user-defined schema. So it's the user's responsibility to say this function takes these 2 inputs and produces 3 outputs, for example. And then using this nice formal specification of the API, we can then generate instances of a data flow graph.
Okay.
And yeah.
So what's the overhead? How is the overhead of let's the user to specify this schema to when the user want to adapt to a library, to fuzz a library?
Yeah, that's a good question. The creating the schema is definitely the most expensive part of writing the fuzzer. And that's the part where you generally spend the most time. For a lot of simple API, if the API is very straightforward, most of the things you're writing are very, very boilerplate. It's like the same code, like it's very simple to define this. And in GraphFuzz, we remove a lot of the boilerplate by letting you just type the function signature. And then it infers a lot of things behind the scenes. And we actually tested during our research. We have a tool in our repository that lets you automatically extract function information using Doxygen. So you can actually go from like C++ source code and then automatically generate a schema. And there are a lot of difficulties with functions that are difficult to define. But in general, we find that 90% of the functions can be automatically inferred in this way. And then the developer just needs to go in and fix the things that are broken.
Okay. Maybe another quick question that, yeah, because this work is about API fuzzing. So actually, there are quite a few works that also target in this similar scenario, like previous, like Randoop. It's also actually to generate different data to fuzz these APIs. So I'm not sure that how is your work and different from this work. Actually, I think in recent, maybe this year's ICST, they also worked to some metamorphic testing to fuzz the C++ library because he can, the author devise some metamorphic relation that they can combine some APIs together to construct some metamorphic relation. So how have you ever evaluated the difference between your tools and these tools? Or yeah, can talk about.
So yeah, so we didn't evaluate against those tools. We have in our paper, we did a pretty extensive survey of some previous approaches to API testing, and we also did a comparison to manually created fuzzers for the Skia graphics library. In general, I think one of the novel components of our work is that because we're integrated with libfuzzer, we can do coverage-guided fuzzing on the API structure. And what this means is that if you generate an API sequence that discovers the target doing something interesting or doing something new, the fuzzer will save that example and it can reuse it and mutate it to generate new examples. And yeah.
Okay. Thank you. Yeah. Yeah. So yeah, we will move to the next speaker and Samartan. That yeah, I listened to your talk. I'm curious that you mentioned that all the prior metrics are not usable, or maybe not that useful that to measure how good that the automatically generated commit messages. So do you have any insights that in the future how to maybe incorporate some key information to form to set up a new metric? Do you have any insight on this? And do you imagine that in the future? I think this is a very useful future if indeed there is a tool, such a tool that can automatically generate commit message that will be useful. So do you think in the future it's feasible that can generate like human those messages written by the human? Yeah.
Yes, so there exists such not one but 3 or 4 such models which actually take commit messages as input and produces which takes code changes as input and outputs a commit message. We our focus was to change the way these models are evaluated and use a new metric which is more reasonable to evaluate commit messages, since commit messages we believe are semantically different from natural language sentences or standard English sentences, and that's why the metrics that were used for machine translation evaluation bit obsolete for evaluating commit messages specifically, and that's why we proposed a new metric that is logmNext, which actually is designed specifically for the sole evaluation. So because it takes factors that we feel should be considered for evaluation of commit message, the length of message, the semantic punctuation, so the differences between a reference and predicted sentence in a test test training data, whatever, that should by punctuations that should be affected by length variations, etc. So keeping all these factors in based instead of the commonly used BLUE metric in practice now.
Okay. Oh, it looks we lost Samerton due to the network signal. Okay. Maybe we can move to the next author. Have some question for Yanjie. Yeah, we can return back when Samerton come back. Yeah. So Yanjie, you present a work about to finding some type errors for to check the deep learning models. So yeah, actually, I'm curious that how is the false positive or the true positive for this technique? Yeah, can you say something about this?
Okay. Currently, Rafty achieves 100% for this issue because we manually verify the error and attach new constraints to this tool and then make it become more and more precise for this issue. And we also manually study the source code to obtain the constraints. And we also use fuzzer to trigger lots of to see the runtime errors. So we could build it more and more robust.
So yeah, because you have the computation of false positive and true positive, so I guess you have a benchmark, a ground truth data set of different.
Yes.
Okay, so this is also done in your this work.
Yes, but this is also done from this work, and the future maybe we will make it more diverse and maybe have a new work. Yeah.
Okay. So as for the type errors, are there any other types of errors you find is also like common that, or is it possible in the future to design such a static checker or for other types of error in your opinion?
In my opinion, currently we only observe we list on the table the common type errors because deep learning models is error and deep learning job errors is a more large topic. It contains many errors from Python, from the environment, from our previous list that. But for deep learning type errors, we only observe the errors and list in the table, and Rafty can solve it. Currently, we didn't see more new type errors for deep learning specific, but the errors from Python we didn't list on it.
Okay. So during research, like do you have you ever find that maybe there could be some inherent errors from the deep learning framework that may also affect
Yes, deep learning models for TensorFlow and PyTorch, they contain some different implementation. So will trigger on a specific framework, but other not trigger, we also list that. For example, the TensorFlow will constrain the dilation and the stress. It has the specific constraint. We think that the framework also has space to improve from these errors. Maybe testing the framework is amazing area. Could pay effort to that.
Okay. Thank you. Okay. Yeah. So yeah, I know Samantha is comes back. So can you continue your prayer answers that you haven't finished? That Samantha.
Yeah, so that's what I was saying. Our model just proposes a new metric, log m next. Was I not audible due to network issues?
Okay.
It was
breaking.
And you cut off. Yeah.
Okay. So what I was saying is that our work proposes a new metric, log m next, and it was prepared or formed keeping in mind the various factors that should affect or impact quality of commit message generation models. And based on that, the metric that we propose, we suggest developers should focus on the use of a more generic metric like ours, the popularly used BLUE metric that is currently in use, because we believe that there exists some difference between semantics of commit messages and standard English language, and hence the evaluation metrics made for evaluating English sentences does not apply to evaluating commit messages specifically. So that's the main issue.
Okay. Thank you. Okay. So yeah. So Jonathan, is there any other question on the chat that haven't been resolved?
None more in the text chat. I have a question for Harrison though, more curiosity on the graph creation, right? So you mentioned the nodes were, I think, functions, and the edges were pretty much inputs and outputs. I guess we're not really doing object-oriented, so they weren't really classes, but some data structure. Or maybe it was C++ or C, I forget.
C++ and C, so they're like
C++
structs.
and C. Okay, yeah. So we have some data structures there, but for finding your valid graphs to test on, what kind of algorithm did you actually use for, creating that graph?
Sure, yeah, that's a good question. So the approach we took in our implementation was basically we have a set of mutations that we can perform that modify one endpoint at a time. And there's sort of a graphic in the paper, but for example, it could be just like swapping one endpoint for a different endpoint in a graph. And it works in two steps. So the first step is we perform some mutation that potentially leaves the graph in like an incomplete state. So maybe we have a method call on the canvas object, but we're missing a constructor for it. So there's like this edge missing. And then the second step is we have something called the edge completion algorithm. And what that basically does is it goes through and it looks for all the edges that are missing, and it generates some subgraph that we can connect at that point that will like complete the graph. So for example, if we have a graph with one edge missing that has type constructor or type canvas, sorry, we can fill it in by adding in our canvas constructor endpoint and then linking it together.
Thanks. That makes sense.
Okay. Yeah. I note we have one audience is also Sanfu. I'm not sure whether I pronounced correctly. I note you are also in this room. Maybe you can also ask something if you have. Okay. Maybe he or she is too shy. Yeah. Okay. Yeah. I think we still have around 5 minutes. Maybe we can quickly let each speaker to have some brief comments that on how do you feel that the work or the field you are working on, and what's maybe the common challenges you think is needed to be addressed in the future? Yeah, maybe just quickly give some insights in this direction. Yeah, so maybe we can start from Rongchen.
Okay. For my work, I think there are two main directions to continue. First is the how to in our work we learned 3 different kinds of loop bound independently. The first direction is how to integrate these 3 bonds together. And the second direction is how to find the more data-driven methods to apply in termination analysis to make the analysis more efficient. Yeah.
Okay. Thank you, Rongchen. Yeah. Yes, Samerton. That you can.
Yeah. So the biggest challenge that we faced was building a human annotated data set for comparison or identification of the 6 factors that we eventually could identify. So because of time constraints as well as due to lack of proficient human annotators, we could not go for building our own human annotated data set. Rather, we had to settle for quite a small sized data set of mere 100. So that was a secondary data set, but we had to settle with it due to time constraints, etc. So the bigger work that lies before us is now to build a larger our own human annotated data set, and finding the right persons who can actually annotate the commit messages is also a big challenge that I feel or we feel will face if we go to do that. Apart from that, another future direction in which we want to work is revising the metric that we have proposed. So a major portion of it has been adopted from the Meteor Next metric devised by Densky and Levy. So we should also improvise our metric in terms of better paraphrase and synonym matching. We should also be careful while removing punctuations from the sentences, and also case folding. So these are the possible ways in which we can improve our work, and we plan to do so in the future.
Okay. Thank you, Samerton. Yeah. So Yinjie, you can talk a bit about there.
Okay, I will share some recent observation. Recently, the deep learning framework become more and more high level. The PyTorch and TensorFlow layer. For example, the domain-specific library like MM detection for CB and Hugging Face for NLP. The high-level framework also will meet the type errors. I think they should treat this problem in more early stage in design stage, because we also observe the hawk if else assert to prevent the type errors. So this can solve the problem in current stage, but it's difficult for user to extend the framework. So we think that although the framework become more and more high level, this error must to meet in the early stage, because the third stage become more and more huge. You tune the hyperparameter. So
okay, good insight. Okay, thank you. So Harrison, you can talk a bit. Yeah.
Sure. Yeah, so I think one of the big challenges with fuzzing in general is that there are a lot of cool tools that people are building, but they're hard to actually apply to real software. Like a lot of these tools work well in an academic setting, but then you try to apply them to like real code and it's just difficult. So that was sort of one of the things we were trying to focus on with our work, is really just to make it accessible and easy for developers to actually learn and start using. And I hope that more future work in fuzzing goes along this route and actually tries to make it easy to use.
Okay, thank you, Harrison. Yeah. Okay, I think the time is nearly reached the end of time. So yeah, so let's thank all the 4 speakers for the wonderful talk, and I think we also have a very good question